Hello everyone, welcome to my talk. I am Sujoy. I am a postdoctoral researcher in the Algorithms Research Group of Université Libre de Brussels, Belgium. I will be talking about Euclidean Steiner 1+ε-Spanners. This is a joint work with Csaba, Tóth. Spanners were originally introduced and studied in the realm of graphs. Let me begin with the graph spanners. Given an edge-weighted graph G, a spanner is a subgraph H of G that preserves the length of the shortest path in G up to some amount of multiplicative or additive distortion. More formally, a subgraph H of a given edge-weighted graph G is a T-spanner for some t greater or equal to 1 if for every pair of vertices, the distance between them in the spanner is at most t times the distance between them in the input graph. And the parameter t is called the stretch factor of the spanner. Here we can see an example of a 6-vertex graph G and a spanner H that has a stretch factor 2. Graph spanners were introduced by Peleg and Schaffer in the Journal of Graph Theory 1989. Spanners are fundamental graph structures that has many applications across domains. Some of them are distributed queuing protocol, compact routing scheme, online load balancing, wireless sensor networks, and many others. In the geometric settings, a T-spanner for a finite point set S of points in Rd is a subgraph underlying of the complete graph that preserves the pairwise Euclidean distances between points in S to within a factor of t. And that is again the dilation factor or the stretch factor. The edge weights of the complete graph are the Euclidean distances between the vertices. Chu in Sausage 1986 initiated the study of Euclidean spanners and showed that for a set of endpoints in the plane, there exists a spanner with linear number of edges and a constant stretch factor. Euclidean spanners have applications across domains. Some of them are topology control in wireless networks, efficient regression in metric spaces, approximate distance oracles. Moreover, Euclidean spanners are relevant in the context of other fundamental NP-hard problems, such as Euclidean traveling salesman problem, Euclidean minimum Steiner tree, etc. There exist various types of geometric spanner constructions. Some of them are bounded degree spanners, alpha diamond spanners, well-separated pair decomposition based spanners, skip lists, locality sensitive, path greedy, gap greedy, etc. The sparsity of a spanner is probably one of the most fundamental parameter of Euclidean spanner and most well studied. So it is the ratio of the number of edges in the spanner to the number of edges in the minimum spanning tree on the point set. And since the spanner is required to be connected, the trivial lower bound for sparsity of a spanner is 1. And in this example, we can see that in the middle figure that the minimum spanning tree of S, but if we want it to be a 2-spanner, then we need to add these 2 orange edges, and then that would be the ratio for sparsity. So when we demand sparse spanners, the question is that how sparse a spanner should be. Preferably, it should contain linear number of edges, but then one can just report a tree, right? But then that will have a very high stretch factor. So simultaneously, one needs to optimize the stretch factor, and the usual demand is that it should be 1+ε for a set S of endpoints. Chu showed that the existence of such a spanner with the stretch factor square root 10, but then in Stock 1987, Clarkson designed the first 1+ε spanner. Moreover, we know that the Delaunay triangulation is a 2.42 spanner, and theta graphs particularly found to be a very effective structure in the context of Euclidean spanners, and that was generalized to d-dimension by Ruppert and Seidel. So the question is that whether the trade-off between the stretch factor 1+ε and the sparsity n epsilon power minus d plus 1 is actually tight. Another fundamental parameter is lightness. So for a set of points S in a metric space, the lightness is the ratio of the minimum weight of a spanner, that is the sum of all edge weights, to the weight of the minimum spanning tree. In this example, we see that if we demand it to be a two-spanner, again, we have to add the orange edges to the minimum spanning tree, and then those weights are going to be in the ratio between this minimum weight spanning tree weight and the spanner weight. So there exists a plethora of work on light spanners. So we know that greedy spanners has constant lightness that was shown by Das et al. In Sausage 93. And it was later generalized to D-dimension in another work in Soda 95. Rao and Smith in their seminal paper in Stock 1998 showed that a greedy spanner has lightness epsilon power minus order D. And they asked the question that what is the best possible constant in the exponent? And more recently, there are general works, for example, Gottlieb in Fox 2015 showed that a metric of doubling dimension D has a spanner of lightness D by epsilon power order D. And Bhore et al. In Soda 2019 showed that greedy spanner has lightness epsilon power order D of a finite metric space of doubling dimension D. All right. So there is a series of work, and then there is a work of Lee and Solomon in Fox 2019 that established the dependencies of epsilon and the constant dimension D in the lightness and sparsity bounds for Euclidean 1+ε spanner. They showed that any 1+ε spanner must have lightness epsilon power minus D and the sparsity epsilon power minus D plus 1 whenever epsilon is omega n power minus 1 by D minus 1. Moreover, they proved that the greedy 1+ε spanner in D dimension has lightness epsilon power minus D times log epsilon power minus 1. In this breakthrough paper, they also observed that the Steiner points behave as a real game changer. They showed that it can substantially improve the bound on lightness as well as sparsity on an 1+ε spanner. So in the sparsity bound, it reaches to epsilon power minus 1 by 2 divided by log epsilon power minus 1. And in the lightness bound, it's epsilon power minus 1 divided by log epsilon power minus 1. However, their construction is for points in the plane, and they also achieved the upper bound for sparsity as well as for lightness. But for lightness, their upper bound for the plane is epsilon power minus 1 by log delta, where delta is the spread of the point set. Moreover, this Steiner points phenomena has been observed in the context of other fundamental network structure. Elkin and Solomon, they observed that Steiner points help to obtain exponential improvement on the lightness of shallow light trees in the single source setting in a general metric space and a quadratic improvement on the lightness in the Euclidean spaces. So our result, we show the lower bound that for a positive integer D and a real epsilon greater than 0, such that epsilon is at most 1 by D, there exists a set S of n points in D dimension such that Euclidean 1+ε spanner has lightness epsilon power minus D by 2 and the sparsity epsilon power 1 minus D by 2. We complement with an upper bound. We show that for points in the plane, there exists a 1+ε spanner with lightness epsilon power minus 1 times log n. So here we stand on Euclidean spanners. So our result, our lower bound, it improves the previous lower bound of Lee and Solomon as we shave one log factor, but then also our result generalizes to higher dimension. In case of upper bound, in this paper, we have an upper bound that doesn't quite match because we are off by log factor for points in the plane, but we managed to shave that log factor in a subsequent work that will be presented in Sausage 21. So now I reach to this lower bound construction, and we prove the following lower bound on the lightness and the sparsity of Euclidean Steiner spanners in RD. So our lower bound construction in RD is a generalization of the planar construction that Lee and Solomon had. However, our analysis is significantly simpler and we use new geometric insight. Just to give a hint of this construction, that one can see the construction in 2 dimensions, and then that is basically a generalized construction to the right in d dimension. The point set will consist of 2 square grids into opposite faces and with the d by square root epsilon spacing. That's all. That's the construction. So let's start with a very basic observation. What we do observe is that for a point pair AB in some dimension D, every AB path of length at most 1 plus epsilon times the length of AB that lies in the ellipsoid with the foci AB and the great axis 1 plus epsilon times the length of AB. Moreover, the points are placed in such a way that the spacing between the points guarantees that we obtain disjoint ellipses for a family of parallel AB pairs. So that helps us actually greatly to us. However, the ellipses may overlap, right? So between 2 different pairs of AB and another pair CD. So then we observe that an AB path PAV of weight at most 1 plus epsilon times the length of AB. This is actually nearly parallel because we have a very little room for error. So this is nearly parallel to AB. So let's define a set of edges E alpha, that is the edge set E in the path PAB, such that the angle is at most alpha with AB. So we proceed with the following lemma that for every I between 1 to 1 by square root epsilon, this EI square root epsilon, this total weight is like greater equal to 1 minus 2 by I squared times the length of AB. We do not go into the details of the proof, and there are several lemmas. The proof of them I will actually omit due to the space constraint, but rather we strictly jump to the corollary. So we observe that every AB path of weight at most 1 plus epsilon times the length of AB contains the edges of direction ABE that is less than equal to 2 times square root epsilon. So of the total weight, that is greater equal to half times the length of AB. Moreover, in each ellipsoid, we count only edges of direction that is within this direction, right? So ABE, and that is at most 2 times square root epsilon, and that implies that no edges is counted twice. So even though there is intersection, it's kind of good. So now I talk about the lightness analysis. So we show that the lightness is omega d epsilon power minus d by 2. The construction, as I said, it's very simple. It's consisting of 2 sets, A union B, and grids on 2 opposite faces of a unit cube with this d by square root epsilon spacing. So the cardinality of this set is theta d epsilon power 1 minus d by 2. Moreover, the weight of the minimum spanning tree of such a point set is theta d epsilon power 1 minus d by 2. So the spanner construction, this is the weight of such construction is the sum of for all AB pair EAB to square root epsilon, and we take the weight of it, which is greater equal to omega d epsilon power 1 minus d. That gives us the lightness, which is like the weight of n divided by the weight of MSD on S. That is greater equal to omega d epsilon power minus d by 2. All right, now we move to the sparsity lower bound. So in case of the sparsity lower bound, our bound is epsilon power 1 minus d by 2. The construction remains same, and in the analysis, so again the point set cardinality is epsilon power 1 minus d by 2, and the spanner construction, this weight same as the lightness analysis, it's epsilon power 1 minus d, and we may assume that n that belongs to Q. So this is also observed by Lee and Solomon in their Fox paper, and therefore this is like at most square root d because it's at most the diameter of Q, and which means that the number of edges in the spanner is greater equal to epsilon power 1 minus d, and that leads to the sparsity because it's en divided by the cardinality of the set S, which is greater or equal to epsilon power 1 minus d by 2. That gives us the desired bound. All right, so with this, I move to the upper bound. Here we prove the theorem 2, and we construct for every epsilon greater than 0 and every set of endpoints in the plane a Euclidean Steiner 1+ε spanner of lightness 1 by epsilon times log n. In order to do this, we need this notion of directional 1+ε spanner. So for a set S of endpoints, assume without loss of generality that the diameter of this set is greater or equal to 1 by 2. So we know, because of the famous result of Few in Mathematica 95, that the weight of the MST on this set is greater or equal to the diameter of this set, and thereby the greater or equal to 1 by 2, and the weight of MST is less than equal to order square root n. So for an interval d of directions, we construct Euclidean Steiner 1+ε spanner restricted to the points pairs whose directions are in d. So we only are kind of interested to the pairs that whose directions are in this certain range. Okay, so formally the definition of directional 1+ spanner is following. A geometric graph G is a directional 1+ε spanner for S and D if for every point pair in S whose direction of AB is in D, the graph G contains an AB path of weight at most 1+ε times the length of AB. Now this is our main lemma, where we prove that for a set S of endpoints in the plane and for the interval D that is within a range of pi minus square root epsilon by 8 to pi plus square root epsilon by 8 of directions, there exists a directional 1+ε spanner G of weight, that is the weight of the minimum spanning tree MST on S, and times epsilon power minus 1 by 2 times log n. We need some notations in order to proceed with this. So for example, per P, that we denote the perimeter of a polygon, and if P is a rectilinear polygon, if every edge is a horizontal or a vertical edge, we know that and the rectangulation of a polygon P is a subdivision of P into axis aligned rectangles. We know that because of the famous result of De Berg and Van Creveld from IPL 94, that one can efficiently compute a rectangulation of weight that is the perimeter of P times log n. Moreover, we can construct a rectangulation of axis aligned bounding box of S with weight that is the weight of the MST times log n. There are two missing components, so I do not give the proof of any of these lemmas, but just to give a brief overview of this, there are two missing components because we sort of rely on the rectangulations and we build the directional spanners inside each of these axis aligned rectangles. So we need two other lemmas that says that let R be an axis aligned rectangles, then for a point set S on the boundary of R, and for an interval within the range of pi minus square root epsilon 8 to pi plus square root epsilon by 8 of directions, there exists directional 1+ε spanner of weight that is the height of R plus the width of R divided by square root epsilon. So and then similarly we have a directional spanner for axis aligned rectangle with the aspect ratio that is within of range 1 by 8 square root epsilon to 1 by 4 square root epsilon, and the interval of direction pi minus square root epsilon by 8 to pi plus square root epsilon by 8. We know that the sum of the weight is going to be order of height of R. All right. So this is a glimpse of the construction, and we eventually use these trees so that between any point pair AB, there is a bypass route, and then we prove in the main lemma that this is fine because this route is going to be, so between any pair AB, it's a series of concatenated paths, and the sum of these path lengths are at most 1+ε times the length of the edge. Okay, so we have given these lemmas, we have all the ingredients to proceed with the main theorem. So we prove that for every set S of n points in the Euclidean plane, there is a 1 plus epsilon spanner of lightness 1 by epsilon times log n. So let's set an integer k to be square root epsilon, and we partition the space of directions into k intervals, uh, where di is 1 minus I minus 1 by k pi to I pi by k for all value of I from 1 to k. So for each I, there exists a geometric graph ni. So we know this from our main lemma, that the weight of this is the weight of the MST times log n times epsilon power minus 1 by 2, such that for every AB pair, if the direction of AB is in DI, then NI contains an AB path of weight at most 1 plus epsilon times the length of AB. All right, so this is how the directional spanner looked like. So we take the union of the networks Ni, and that we just argued about, like one particular Ni for every value of I to n. So now the weight of n is basically the summation from I equal to 1 to n, ni the weight of ni, and that is at most k times the order of the weight of the MST times log n divided by square root epsilon, which is again at most order of MST of s times log n divided by square root epsilon. So the question is that, can't we remove this log n factor, at least not with this approach, because this log n factor is coming because of these rectangulations of the rectilinear polygon that we are doing on order n vertices. So one may ask the question that why don't you do any other type of subdivisioning, for example, subdivisioning into convex faces? Well, maybe it is possible to improve the log n, but we know that it won't be possible to improve it more than log n factor, because there exists this result of Dumitrescu and Tóth from Algorithmica 2011, where we know that every simple polygon P with n vertices admits a convex subdivision of weight. That is the perimeter of P times log n divided by log n, and this is the bound that is sort of best possible. This is the summary of our results in comparison to the state of the art before this work, and that was mostly from Lee and Solomon. So we have an improved lower bound and that is generalized to any dimensions, and then we have an upper bound where we are off by factor log n, and that is only in the plane. Here I would like to point out also that Lee and Solomon in another work recently, they have a result that is for dimensions d greater or equal to 3. They have this upper bound that is epsilon power minus d plus 1 by 2, almost close to the improved lower bound. Okay. So as a future work, the first question that comes from this line of work or this plethora of results, that whether there exist Euclidean Steiner 1+ε spanners for a finite set of points in d dimension with the lightness to be epsilon power minus d by 2, because now we see it with the new light of the lower bound. So we achieved this for points in the plane, and that will be presented in a new work that is recently accepted to Sausage 21. So stay with us and listen to our talk. And moreover, we conjecture that Euclidean Steiner 1+ε spanner cannot simultaneously attain both the lower bounds for lightness and sparsity together. So exploring these trade-offs between the lightness and sparsity is an interesting open problem. The another direction is the plane spanner, and we know that because with the help of Steiner points, any spanner can be made planar, because one can introduce a Steiner points at the crossing of the junction. However, it can blow up the sparsity, because the number of Steiner points that would be required would be quadratic. We can have quadratic many intersections. So bound the sparsity of a plane Steiner 1+ε spanner is an interesting question. Angles and directions, they played a very critical role in our construction. So we would like to pose the question of derive upper and lower bounds on the lightness and sparsity of Steiner 1+ε spanners in other inner product spaces. All right, so with this, I conclude my talk and thank you for your attention.